In the early years of the 20th century, as steel monsters began to roll across battlefields, the world's armies faced a new problem. Heavy armor had rendered the rifle obsolete against tanks, and artillery was too slow to redeploy. Soldiers on the ground needed something portable, something that could punch through metal and even the odds. The story of that idea would travel from laboratories in Europe to jungles in Asia, and eventually to almost every war zone on Earth. It began in 1931 in the Soviet Union, where engineers were experimenting with a shoulder-launched weapon known as the RS-65. It was primitive, unreliable, and lacked the shaped charge warhead that would later define modern anti-tank weapons. The technology was too early for its time. The concept was promising aim, fire, destroy, but the execution lagged behind. Still, those experiments planted a seed that would wait 3 decades to bloom. The real breakthrough came years later, during the chaos of the Second World War. Across the Atlantic, American engineers introduced a simple, almost elegant invention: the bazooka. It was a lightweight, tube-shaped launcher capable of firing a rocket propelled by a small motor. More importantly, it carried a shaped charge explosive designed to burn through armor using concentrated energy rather than brute force. When German forces captured several bazookas early in the war, their reaction was both predictable and immediate. They believed they could do it better. The result was the Panzerschreck, literally meaning tank terror. It was larger, more powerful, and capable of punching through 200 millimeters of armor, enough to make even the most confident Allied tank crews sweat. The Panzerschreck, however, was not without problems. It required a trained crew, and the weapon's backblast could be deadly to anyone standing too close. Germany's engineers, practical as ever, decided they needed something smaller, cheaper, and simple enough for any soldier to use. It was disposable, one shot only. The earliest versions were limited to about 30 meters of effective range, barely the length of a city street, but later models stretched beyond 100 meters, and their warheads grew larger and more efficient. Plans for an even more advanced Panzerfaust. 250 were already drawn up before the war's end, but the collapse of Nazi Germany left them unrealized. Meanwhile, the Soviet Union was watching. Throughout the war, its soldiers relied mostly on anti-tank rifles and field guns, effective but cumbersome. The idea of a soldier carrying a compact launcher that could defeat armor fascinated Soviet engineers. When the guns fell silent in 1945, the Soviet design bureaus began dissecting everything the Americans and Germans had built. They didn't copy any one weapon directly. Instead, they tried to combine the best elements from all sides. The result was the RPG-1, a crude but conceptually brilliant experiment. It featured a 1-meter-long launch tube, a sharply angled pistol grip, and a wooden shield designed to protect the operator from the rocket's heat. Though the design looked promising, it suffered from serious flaws. Its range was short, its accuracy questionable, and the rocket's reliability poor. Tests showed that sometimes it failed to ignite, and sometimes it exploded too early. Soviet soldiers joked that the RPG-1 was as dangerous to the shooter as to the target. Yet in those failures lay the blueprint for success. The following iteration, the RPG-2, solved most of the earlier problems. It introduced a more powerful propellant charge, a longer effective range, and a sturdier warhead with 80 millimeters of caliber. The weapon could now penetrate roughly 225 millimeters of armor, enough to disable most tanks of the early Cold War era. By 1954, it had entered service with both Soviet and Chinese forces, marking the first real step in a legacy that would stretch far beyond its creator's imagination. Its debut in combat would come soon after, in the thick jungles of Vietnam. There, the simplicity of the launcher became its deadliest advantage. American patrols quickly learned to fear the small puff of smoke that preceded a rocket streaking from the foliage. Lightly armored vehicles, such as the M113 personnel carrier, could be torn apart by a single hit. Even heavier tanks, like the M48 and M60, were vulnerable when struck in the right spot. The RPG-2 was not just a weapon, it was an equalizer. It gave lightly armed fighters the means to challenge machines worth millions. Still, engineers were not satisfied. Each success invited a new question. How much further could they push this design? Experiments with larger warheads, stronger propellant charges, and new optical sights followed. The intermediate model, the RPG-4, was never widely produced, but it served as a bridge toward the weapon that would define the next 6 decades of warfare. By the dawn of the 1960s, the Soviet Union had refined the formula into something extraordinary: a reusable, rugged, and brutally effective anti-tank launcher. It was as much a symbol of industrial pragmatism as of military innovation. Unlike Western designs, which often favored complexity, the Soviet philosophy valued simplicity above all. A weapon should work even in mud, in sand, in the freezing cold. When the RPG-7 entered service in 1961, it did so not as a marvel of technology, but as a triumph of logic. Its steel tube was only a few millimeters thick, yet resistant to rust. It required no delicate maintenance and could fire again and again with minimal care. Ammunition was loaded from the front, secured by a simple mechanical notch. Its warhead extended beyond the diameter of the tube, allowing for a larger explosive charge without increasing the launcher's bulk. The philosophy behind it was almost poetic in its brutality. If you cannot afford to build perfect machines, build weapons that destroy them instead. The Soviets had created not just a launcher, but a tool of asymmetry, one that would shift the balance of warfare for generations. In dusty training grounds from Siberia to the Caucasus, young conscripts learned to handle the new weapon. They were told that even the mightiest Western tanks could be defeated with a single, well-placed shot. The numbers etched in their manuals: 200 meters of effective range, over 200 millimeters of armor penetration, were not just statistics but promises. The RPG-7 had arrived quietly, but its echo would soon circle the world. From the frozen steppes where it was born to the tropical jungles where it first drew blood, it embodied a paradox that would haunt modern warfare. The simplest inventions often outlive the most sophisticated ones. The path from an awkward prototype to a battlefield staple rarely follows a straight line. Designs stumble, parts fail, and ideas that seem brilliant in theory collapse under the weight of real combat. The evolution of the handheld anti-tank launcher was a patient, iterative process, driven by a single obsession: how to make a weapon both simple and lethal. Engineers learned fast that solving one problem often revealed another, and each new version became a compromise between recoil, weight, reliability, and the brutal arithmetic of war economies. The first practical Soviet attempt retained the name RPG, followed by the number 1. It was little more than a laboratory sketch given metal and wood. The long launch tube forced soldiers to lug unwieldy hardware across trenches and into ruined buildings. The wooden handguard offered protection from heat, but provided little against the realities of combat. The warhead lacked the optimized shape and lining necessary to produce a focused metal jet, and the propellant charge proved inconsistent in cold weather. Trials showed that a well-trained crew might deliver a useful strike at very close range, but in the chaos of a firefight, those ideal conditions were rare. Rather than abandon the concept, designers returned to fundamentals. The RPG-2 represented a new philosophy: shrink what could be shrunk, reinforce what must be reinforced, and tolerate imperfection everywhere else. The launch tube remained a mainstay, but it was shortened and made lighter. The grip geometry changed so that ordinary conscripts could shoulder and fire the weapon with minimal instruction. Engineers experimented with different propellant charges and delivery systems until they found a combination that produced a more stable flight and longer reach. The warhead grew in diameter and in practicality. An 80mm shaped charge became the baseline for penetration goals that matched the armor of the era. The improvements were not purely mechanical. Manufacturing doctrine shifted toward modularity and mass production techniques that favored simple tooling over exquisite tolerances. Factories across the Soviet sphere learned to make barrels, boosters, and warheads at scale. This approach reduced unit costs and made replacement parts easier to store and ship. The doctrine that shaped the design was political as much as technical. A weapon that could be produced cheaply in large numbers fit the strategic needs of a state that planned for attrition rather than surgical engagements. Armies that could flood a battlefield with thousands of identical weapons forced opponents to rethink armor doctrine and logistics. Field feedback then shaped subsequent models. Soldiers reported how the launcher behaved under stress, how the sighting systems performed at dawn and dusk, and how often a dud round became a ricochet hazard. These practical observations led to design choices that would become signature traits. The launcher would accept front-loaded projectiles, simplifying the loading process in cramped spaces. A simple notch would lock the projectile in place with minimal moving parts. The rear of the tube would be engineered to direct backblast in a predictable cone so that crews could learn safe firing positions. These were small changes, but they mattered greatly when dozens of weapons were fired in succession. By the time the next generation arrived, engineers had embraced the necessity of multiple warhead types. The original emphasis on armor penetration proved insufficient in the varied forms of modern conflict. Urban fights demanded munitions that could demolish concrete and clear rooms. Anti-personnel fragmentation rounds offered utility when the goal was suppressive fire rather than vehicle kills. Thermobaric warheads emerged as a terrifying answer to fortified positions, releasing fuel aerosols that detonated to create intense heat and overpressure in enclosed spaces. The choice to diversify rounds turned a mere anti-tank tool into a versatile infantry asset. The late 50s and early 60s saw the culmination of these efforts. The model that would be known to the world combined rugged simplicity with a surprising flexibility. Its tube was thin-walled and chrome-lined, resisting corrosion and surviving neglect. The front-loaded projectile design remained, but the warhead profile was optimized for shaped charge performance. Stabilizing fins folded away during the initial boost and deployed once the projectile cleared the launcher, ensuring a steadier flight and better accuracy at reach. The firing sequence adopted a two-stage logic: a small booster to clear the tube and a sustainer rocket to drive the warhead toward the target. This arrangement allowed for a compact launcher while permitting larger and more effective warheads. Military schools shortened the time needed to bring a recruit to functional competence. Where earlier weapons required extended drills, the newer launchers could be put to basic use after a few hours of familiarization. Manuals emphasized range estimation without complex optics, use of natural cover, and the avoidance of enclosed spaces during firing. Unit tactics taught teams how to position spotters and loaders, how to withdraw after firing, and how to exploit the weapon's strengths in ambushes. This human factor was crucial. A design is only as effective as the people who employ it. Comparison with other systems deepened the appreciation for the new launcher's philosophy. Western anti-tank options often relied on more complex sighting equipment or reusable shoulder tubes that demanded regular maintenance. The Soviet style preferred robustness and redundancy. If a sight failed, iron sights remained usable. If a launcher was dented, it still fired. The ethos was simple: make weapons that will not be a burden to the nation, in pieces and men in poverty. Manufacturing scale proved decisive. Factories that once produced field guns learned to repurpose lines for launch tubes and warhead casings. Supply chains adapted to need, and the weapons arrived not only in national arsenals, but also in the hands of allies and proxy forces. This diffusion was intentional in some quarters and inadvertent in others. Exported as a strategic good, supplied as a gesture of alliance, or acquired second-hand on a black market, the launcher found its way far beyond the borders of its birth state. Even as the design stabilized, enemies found ways to adapt. Spaced armor, applique plates, and explosive reactive tiles arrived as countermeasures. Each counter invited new warhead concepts, including tandem charges designed to defeat reactive armor by using a precursor charge to neutralize the countermeasure before the main charge struck. This cat and mouse of offense and defense would become a theme carried into future decades. But the core lesson remained constant. A simple, well-made launcher placed the power of armor defeat into the hands of infantry in ways that reshaped tactics and justified mass production. By the time the launcher entered widespread service, it was less a single weapon than a family. A basic tube and a catalogue of warheads that could be mixed and matched to meet the demands of widely differing battlefields. Its success owed as much to factory discipline and doctrinal clarity as to any single engineering breakthrough. The weapon's design journey was a study in practical problem-solving. Reduce complexity where possible, and concentrate sophistication where it mattered most. The result was a tool that could be taught quickly, produced cheaply, and used lethally across a vast range of conflicts. The launcher looks deceptively simple. A hollow tube, a trigger, a sight, and at the rear, a cone that eats heat and directs the angry breath of the engine away from the shooter. Yet within that modest silhouette is a choreography of physics and engineering that turns a shoulder-held device into a weapon capable of rewriting the life of a vehicle and the fate of the men inside it. Understanding how it works requires following the projectile from cradle to impact, and then listening to what happens when shaped explosives meet steel. The projectile is inserted nose first and slides back until a shallow notch in the tube locks into a groove on the round. This front-loaded arrangement allows the warhead to be larger than the tube, an elegant trick that keeps the launcher compact while permitting a heavy, effective, explosive charge. A small booster charge at the base of the warhead performs the initial task. When the trigger is pulled, the booster, essentially a blank cartridge, expels the round from the tube to a safe clearance distance, typically about 11 meters. At that point, a sustainer rocket ignites, accelerating the projectile to its cruising speed. The sustainer preserves momentum over distance, while folded fins pop out to stabilize flight, turning a tumbling brick into an arrow. The backblast is a defining feature and a tactical constraint. The launch sequence produces a cone of high-temperature, high-pressure gas directed rearward. For safe operation, an operator needs clear space behind him, measured in meters rather than centimeters. Firing from enclosed structures or with troops too close behind invites injury or worse. This danger-shaped doctrine, teams developed firing drills, angles of withdrawal, and staging areas designed to minimize friendly casualties. The backblast also means that firing positions are often chosen for clearance rather than concealment, a compromise between stealth and survivability. At the heart of the most feared warhead is the shaped charge. Its principle is both elegant and merciless. A conical cavity lines the inside of the warhead nose. That cone is backed by a thin metal liner, often copper. When the explosive surrounding the cone detonates, the energy collapses the liner inward, forming a jet of metal fragments that travels downrange at extreme velocity. This jet concentrates energy into a small area, eroding armor by sheer localized force rather than by blunt kinetic impact. Typical jet velocities, when the effect works well, reach the order of 10,000 meters per second against a homogeneous steel plate. A well-made shaped charge can punch through armor measured in hundreds of millimeters. In practice, early effective warheads could breach around 260 millimeters of rolled homogeneous armor on a direct hit, a figure that in the early Cold War equated to frontal vulnerability for many contemporary tanks. Not every round behaves as intended. Real life imposes messy probabilities. Temperature extremes, rough handling, and manufacturing variants can convert a lethal projectile into a harmless dud, or worse, a premature detonation that maims the operator. To mitigate these risks, engineers added safe and arming mechanisms. A plastic cap and safety pin on the nose prevent the fuse from engaging until the round is deliberately armed. There is also a self-destruct timer set into many designs so that if a projectile fails to strike a target, it will render itself inert after a set distance. In many models, this self-destruct distance is set at 900 meters. The timer reduces unexploded ordnance, returning to the battlefield as hazards, but it cannot remove every risk associated with sloppy storage or improvised use. Variants expand the launcher's role far beyond armor defeat. Fragmentation rounds trade penetration for blast and shrapnel, useful for clearing open positions and inflicting casualties among exposed infantry. Thermobaric munitions introduce a different kind of violence. On impact, a small charge disperses a fuel aerosol and milliseconds later ignites that cloud to produce intense heat and a sustained overpressure. A room that survives the initial detonation collapses under the pressure wave and consuming heat. Thermobaric rounds thus became a weapon of choice for bunker clearing and urban assault, yet their use raises acute moral questions because of the suffering they inflict in enclosed environments. Tandem warheads represent a technological counter to protective innovations. Explosive, reactive armor arrived to blunt the shaped charge's effectiveness. Reactive tiles detonate outward when struck, disrupting the shaped charge jet. A tandem warhead counters this by placing a small precursor charge at the nose of the round. The precursor detonates first to neutralize the reactive tile, and the main charge follows fractions of a second later to strike the underlying armor. This sequence demands precise timing and reliable fusing. It is an elegant solution to a deadly problem, but it also increases complexity and cost. Guidance in the strict sense is absent. These systems are aimed and fired by human eyes and hands. Some later models incorporated rudimentary optics with reticles, graduated for range, but effective engagement depends on range estimation. Wind and target motion. In practice, the effective precision envelope sits well below the theoretical sighting distance. Most trained crews expect real first-hit probability against point targets at ranges under 300 meters. Beyond that, the weapon becomes an area effect tool more than a precision instrument. The operation is often a team act. One soldier shoulders and fires, while another carries spare rounds, checks, fuses, and watches the flanks. Teams learn to coordinate. A spotter calls range. A loader prepares the next round. The shooter slings, aims, and fires, and then the unit melts back into cover. In ambushes, this choreography becomes lethal. A sudden puff of smoke in foliage, a short, distinctive scream of a rocket, and a vehicle struck in its weaker flank is often immobilized or destroyed outright. Many successful attacks rely less on one perfect shot and more on volume and coordination. Multiple strikes to the same vehicle increase the chance of catastrophic kill, or at least mission kill. There are trade-offs and constraints that never disappear. The backblast limits indoor or very close quarters use unless the team accepts the risk. Tandem charges raise costs and complicate logistics. Thermobaric rounds satisfy tactical needs but inflict terrible collateral damage. Reliability depends on storage, maintenance, and care that are not guaranteed in every theatre. Yet for infantry in need of a compact, transportable, and versatile anti-armor option, the system fills an enduring niche. It takes only a modest investment of resources and a short training cycle to place a potent tool of destruction into the hands of countless irregular fighters. That fact explains much of the weapon's ubiquity and the fierce debates it sparks about force, protection, and the limits of modern armor. The machine and its warheads do not decide policy, but they shape the options available to commanders and to the people who must survive the wars they make more lethal. When a weapon is cheap, light, and effective, geography ceases to be a limit. The launcher that had been refined on Soviet proving grounds found a stage far larger than any single nation. It arrived first in environments where its virtues mattered most. Dense vegetation, narrow streets, and improvised tactics turned the launcher from a technical curiosity into a symbol of asymmetric warfare. In those places, soldiers with little in the way of heavy logistics could inflict disproportionate damage on mechanized forces armed with expensive machines. Its baptism of fire arrived in the humid green of Southeast Asia, where jungle and ambush suited it perfectly. Small units learned to place teams along likely approach routes and to wait until a vehicle filled a kill zone. One well-timed shot could destroy the engine, blow away a track, or set off ammunition inside a cramped personnel carrier. Infectious fear spread among crews because the weapon was invisible until the smoke and scream of the rocket announced the strike. Light armored vehicles designed for mobility rather than protection were particularly vulnerable, and convoys learned to disperse, to change approach routes, and to avoid choke points that turned them into predictable targets. The pattern repeated itself in the deserts and cities of the Middle East. In open terrain, crews relied on concealment and sudden strikes. In towns and dense urban networks, the launcher prospered. Fighters established firing positions on building rooftops or in upper stories so that the weapon could be aimed at weak roof armor or turret tops. Vertical geometry changed the calculus of defense because many tanks have thinner protection on their roofs. A rocket delivered from above had an advantage that frontal armor could not meet. Urban ambush became choreography. Teams used snipers and forward observers to spot targets. Spotters called range, loaders passed the next round, and shooters fired from prepared positions that offered both a clear line of sight and an escape route. When multiple teams coordinated strikes, the results were catastrophic for the defenders. The weapon also flourished where non-state actors and insurgent groups found advantages in a low barrier to entry. Because the launcher could be taught and produced at scale, arsenals spread beyond the control of governments. Some transfers were deliberate, a strategic export to allies and proxies. Others were chaotic, the result of collapsing states, corrupt supply chains, or looted depots. It moved through broker networks and across porous borders until it became part of the standard armament of many irregular forces. It changed incentives for international actors. States that once relied on heavy armor began to adapt doctrine and procurement to anticipate urban and guerrilla environments. Convoys rearranged formations and dismounted patrols augmented vehicles with infantry screens. Armor alone would no longer guarantee safety. On the other side, fighters without heavy industry could still pose existential risks to mechanized formations. The balance of initiative shifted toward those who could blend into a population and strike with concentrated, sudden violence. The psychological effect has always been as important as the physical one. A crew that knows its vehicle might be disabled by a single cheap projectile behaves differently. Caution replaces aggression. Speed slow. Routes multiply. Commanders worry not only about casualties and hardware, but about morale. The launcher became not only an instrument of destruction, but also a tool for shaping behavior on the battlefield. It forced larger forces to expose themselves to new vulnerabilities and to expend resources on countermeasures that had to be carried, maintained, and replaced. The weapon's ubiquity was also visible in more brutal examples. Urban fighting in the North Caucasus showed how columns could be torn apart when ambushes exploited urban geometry and local knowledge. Mechanized formations accustomed to open terrain found themselves in streets where elevation and concealment negated much of their advantage. The attacker did not always need to destroy every vehicle. Immobilizing a tank by stopping its drivetrain or breaking its turret ring was often sufficient. Immobilized machines became liabilities, public monuments to failure that required recovery operations and left exposed flanks that shaped subsequent fights. Modern conflicts revealed new permutations of the weapon. In some theaters, commanders organized massed volleys of rockets to saturate active protection systems and to exhaust the limited number of interceptors carried by those defensive suites. When several projectiles arrived within short intervals, the probability of at least one getting through increased. That tactic turned numbers into a strategy. Other adaptations married the warhead to new delivery systems. Small unmanned aerial vehicles carried shaped charges into angles that ground shooters could not easily reach. A drone could approach quietly and place a warhead on a vehicle roof with an accuracy that eliminated the disadvantage of low impact velocity. These innovations retained the same fundamental logic, but multiplied the contexts in which the weapon could be used. The social cost of diffusion was severe. Weapons that spread into neighborhoods, into militias, and into criminal networks blurred the line between combatant and civilian. A launcher repurposed for criminal violence elevated the stakes of policing and deepened community trauma. Families learned that a cheap projectile could kill not only soldiers but also neighbors and kin. Reconstruction had to reckon not only with shattered structures, but with the psychological imprint of sudden destruction. In many places, the presence of such weapons delayed the recovery of civil life because their existence sustained fear long after active battles subsided. Some states pursued tighter export controls and improved monitoring of arms transfers. Others increased support for armor modernization and active defense research. Yet these measures often lagged behind the speed at which the launcher proliferated. The reality remained that a production line in one country could, through official transfers and unauthorized channels, seed conflicts thousands of kilometers away. The weapon's material simplicity meant that even modest industrial capacity could produce components or replicas. For commanders and civilians alike, the launcher altered expectations. Battles would be fought not only in fields and on roads, but in alleys, stairwells, and on the roofs of apartment blocks. The presence of such a weapon demanded new tactics and, crucially, new humility about the limits of technology. No armor was absolute. No defensive system proved perfect. The proliferation of a cheap, effective weapon rewrote the rules of engagement in countless theaters, compelling armies to adapt and societies to live with a new normal, where danger could come from a single, unremarkable tube and the men who carried it. The arrival of a cheap and effective threat forced defenders to invent responses that ranged from the improvised to the cutting edge. At first, the answers were humble and ad hoc. Crews hammered together wooden planks, stacked sandbags, and lashed scrap metal to hulls. These measures worked on a principle as old as siegecraft. Add layers that break or disrupt the attacker before it reaches the critical target. A shaped charge that detonated a short distance from the outer skin lost much of its destructive focus. Spaced armor, in its most rudimentary form, tended to detonate or deform the jet prematurely. In many early encounters, a sheet of timber, or even a box filled with gravel, provided enough of a buffer to turn a lethal hit into a damaging but survivable one. Those improvised fixes were never elegant and could be dangerous in their own right. Extra weight upset suspension and mobility. Uneven loads reduced speed and increased mechanical failures. Crews carried the added burden of carrying and mounting clumsy protections while under fire. Yet the trade-off was often acceptable. Mobility could be sacrificed for survivability because immobilization in a combat zone often meant destruction or capture. The improvised approach revealed a basic truth. Cost-effective offense produces pressure for cost-effective defense, which cascades into tactical change. The industrial answer evolved in several strands. One approach was to increase passive protection by bolting additional plates to vulnerable areas. Applique armor and add-on plates thickened exposure points and were particularly useful on side and rear arcs, where original designs often left weaker steel. Another line of response involved cage armor, which became known by many as slat armor. A grid of vertical bars or light metal cages placed at a calculated distance from the hull would cause a shaped charge warhead to behave unpredictably. The blast interaction occurred away from the main armor, reducing penetration. Slat armor had the virtue of being relatively light, cheap to manufacture, and quick to install. It did not solve the problem entirely, but it forced attackers to aim for different points and to risk longer exposure to return fire. A more dramatic solution was explosive, reactive armor. These were tiles mounted on a plate that contained a thin layer of explosive. When a shaped charge or certain kinetic round struck the tile, the explosive detonated outward and blew the outer layer away. The motion disturbed the shaped charge jet and reduced its penetration. Reactive armor worked well enough to change the calculus of engagement. It was particularly effective against single-charge warheads, and in many theaters it saved tanks that otherwise would have been lost. Yet reactive armor introduced its own problems. The tiles could injure nearby dismounts when they detonated. They added mass and complexity to logistics because damaged tiles needed replacement. Furthermore, tacticians soon observed ways to defeat reactive armor. Attackers adapted tandem charge munitions that used a small precursor to detonate the reactive tile and the main charge to follow through. This iterative escalation made clear that every defensive innovation carries the seed of a new offense. The next chapter of defense moved into electronics and speed. Soft kill systems sought to confuse or deny the attacker by obscuring the target or by disrupting guidance. smoke screens designed to mask infrared or visual acquisition, laser dazzlers that blinded seekers, and active jamming systems all belonged to this category. Soft kill measures had the advantage of being less likely to cause collateral harm, but they were useful mainly against guided munitions. Unguided rockets and hand-launched rounds did not rely on seekers. They were aimed by sight rather than electronics, which left soft kill measures of limited use against the shoulder-fired threat. That limitation drove development toward hard kill solutions. Active protection systems were developed to detect incoming projectiles and then to physically intercept or deflect them before they struck armor. These systems used radar or other sensors to give a warning and then launched counter-munitions that detonated near the incoming warhead. In practice, hard kill systems created a brief cloud of fragments or a directed blast that broke up the shaped charge or shifted its point of impact. They represented a profound shift. For the first time, an armored vehicle could mount defenses that operated in the last few meters of flight, converting passive resilience into proactive interception. Hard kill technologies offered a powerful promise, but their limitations were real and consequential. Sensors sometimes failed. Counter-munitions had limited inventories and could be exhausted by waves of incoming fire. Installations of active protection raised operational questions about the safety of accompanying infantry. A system that detonates close to a vehicle risks injuring troops riding on or operating beside it, which meant commanders often had to decide when to enable and when to suppress the system. The rules of engagement and the geometry of combat forced compromises. In many documented engagements, crews disabled or limited active defenses to avoid friendly harm, which left them vulnerable. Others accepted the risk and operated the systems in automatic mode, with the attendant chance that an interceptor might harm nearby non-combatants. The economics of defense also mattered. Advanced protection systems were costly. Not every army could equip every vehicle with them. Production and maintenance budgets constrained deployment and favored high-value assets that created a stratified battlefield. Frontline formations with advanced active protection could survive heavy exposure while lighter elements remained vulnerable. Commanders had to decide where to allocate limited protections and how to adjust tactics accordingly. Massed rocket attacks sought to saturate active protection by sending multiple rounds within the short time window the system required to engage. Combining ground-based volleys with aerial delivery from unmanned drones created complex attack patterns that stretched sensors and interceptors. The cost-effective attacker tactic became one of volume and surprise. Swarming tactics exploited sensors, reaction times, and logistic limits in urban combat. Attackers carved firing positions that maximized cover and minimized the chance of interception. They aimed at roof and rear arcs where armor was thinner, or they targeted support systems and tracks rather than frontal armor, seeking to produce mission kills rather than total destruction. The net result was a continuous cycle. Designers created armor to meet a new threat. Attackers invented warheads and tactics to defeat that armor. Defenders built new countermeasures and then modified doctrine to cope with the next innovation. Each new device changes how wars are fought and who pays the price. Defensive innovation also left a quieter legacy. It changed strategic thinking about where and how to use armored vehicles. Armored columns became more cautious in urban environments. Rapid advances across open ground required new thinking about screening, reconnaissance, and dismounted infantry support. The presence of a cheap anti-armor tool imposed a constant constraint on initiative. The choice to deploy armor into a contested environment now involved not only vehicle survivability, but also the logistics of sustainment and the political cost of attrition. In that sense, the story of protection is also a story of the limits of power. When a weapon endures for decades, its story becomes less about a single design and more about a pattern of adaptation. The launcher that began as a pragmatic Soviet answer to post-war realities did not simply persist because of nostalgia. It persisted because its logic fit an enduring set of constraints: low cost, ease of manufacture, minimal training requirements, and flexible lethality across many contexts. That combination made it a durable tool of war and a persistent problem for those who sought to stop it. Technological branches sprouted from the original concept. Tandem warheads solved the problem posed by reactive tiles. Advanced standoff charges extended the effective penetration against sloped or composite armor. New propellant chemistries improved consistency in extreme temperatures, and treatments extended shelf life for munitions stored in distant depots. At the same time, designers grafted the warhead onto new delivery platforms. Integration with small unmanned aerial vehicles created a hybrid threat. Drones could approach quietly and strike from above, where armor was thin and angles unprotected by traditional defensive arrays. The marriage of a shaped charge to a remotely piloted platform multiplied the launcher's tactical options while reducing exposure to counterfire. These innovations forced armor designers and commanders into difficult choices. Spending on active protection suites and advanced composites became a necessity for forces that expected to face asymmetric threats. Yet the expense was considerable. Equipping a single vehicle with modern interceptors and sensor suites required budgets far larger than covering simple applique plates. The result was a stratified battlefield in which the most precious assets received layered defenses and lighter formations remained vulnerable. Commanders had to weigh whether to risk expensive platforms in contested environments or to rely on numbers and tactics to limit exposure. The economic calculus extended beyond procurement. Training, logistics, and maintenance all shaped how effective any defensive measure would be. Active protection systems demanded spare interceptors, calibration, and technical crews. Reactive armor tiles needed replacement after use. Even improvised measures imposed costs in mobility, fuel consumption, and wear on suspension systems. In theaters where budgets were limited, the decision often favored tried and true simplicity, which in turn prolonged the life cycle of the small anti-armor launcher that had started it all. There is also a human dimension to the legacy. The weapon made asymmetric struggle more feasible, and thus reshaped political realities. Non-state actors could now threaten conventional forces more credibly. That reality influenced strategies from proxy support to insurgent doctrine. The presence of a cheap but lethal threat shifted bargaining power on the ground and complicated diplomatic efforts to stabilize conflict zones. Neighborhoods once safe became places to avoid, and rebuilding required more than concrete and steel. Trauma shaped generations and hampered recovery long after ceasefires were signed. Ethics and law responded unevenly. The wide availability of a weapon suited to both military and punitive uses blurred lines in conflict. Thermobaric variants and munitions, optimized for urban destruction, raised questions about proportionality and civilian harm. International debates surfaced about transfer controls, about accountability for arms brokers, and about how to prevent illicit flows without restricting legitimate state procurement. Yet enforcement lagged. Borders are porous in many regions, and shadow markets thrive when demand exists. The result was a cycle in which technology moved faster than regulatory frameworks. The tactical theater continued to evolve. Swarming attacks and combined arms platoons attempted to overwhelm defenses or to create multiple axes of threat. Teams learned to mix ground-fired volleys with airborne small platforms, to use suppressive fire to distract active defenses. In turn, defenders refined sensor fusion and attempted to build countermeasures specifically tailored to low-signature, low cross-section threats. Doctrine, training, and intelligence mattered as much as hardware. A persistent irony is that the most advanced systems remain vulnerable to the simplest tactics. Hard kill interceptors are susceptible to saturation. Soft kill measures are ineffective against unguided, human-aimed launches. Complex electronics are vulnerable to weather, terrain, and deliberate countermeasures. For armies that rely on technology, the lesson is cautious humility. No system solves the strategic problem alone. Combined measures, doctrine, and local intelligence form the best defense. And even then, vulnerability remains. Looking forward, the most likely path is not a single breakthrough that makes anti-armor shoulder weapons obsolete. Instead, the foreseeable future looks like ongoing adaptation. Warhead designers will seek new liners and shaped geometries. Propulsion improvements will aim for greater accuracy without sacrificing compactness. Integration with artificial intelligence on both sides will refine targeting, threat detection, and countermeasure activation. Legal and regulatory efforts may tighten some flows, but cannot completely stem the tide of diffusion without broad political solutions to the conflicts that create demand. Perhaps the most important legacy is conceptual. The launcher crystallized a principle about modern conflict. Asymmetry often wins, where cost-effectiveness, adaptability, and human ingenuity intersect. Economies of force can outmaneuver economies of scale. The cheap launcher did not simply defeat armor by brute force. It forced a rethinking of mission design, rules of engagement, and the political calculus of deploying expensive assets into contested spaces. For the individuals who lived through encounters with the weapon, the memories are sharp and unforgiving. Tank crews recount the suddenness of an impact, the way internal alarms and smoke can change a mission in seconds. Infantry veterans remember the terror of urban streets that conceal shooters on every rooftop. Civilians recount homes reduced to rubble by warheads that were designed for armor but found their cruel efficiency in concrete and timber. These human stories give the technical narrative its moral weight. In the end, the story is not solely about a tube and its projectiles. It is a story about adaptation, about how technology and tactics bend and break under pressure. It is a story about the limits of protection and the costs of offense. And it is a story that continues because the pressures that created the launcher remain with us. As long as disparity exists between the resources of combatants and the ingenuity of their adversaries, tools that offer cheap, scalable lethality will continue to shape battlefields and to force hard choices upon commanders, states, and societies.